Hi, I'm Jessica and I'm from Dark Papoy for FIT3183 and I will explain my project in the functional adversarial attack enhancement. So basically, what is functional adversarial attack? It's different to the usual additive threat model. And so instead of adding perturbations to our input, we are applying functions to the input. So this will be the result of the perturbed input by applying function f. For example, in this assignment, I am using the open source RecolorAdv. So what this does is that taking a certain pixel in here, we apply a function that uses this vectors projection to map this to the adversarial pixel. So in this case, the model, the target model that previously is able to classify this as an airplane will classify this as a dog after the function f is applied. And the basic idea, if let's say we want to change all the red pixels in our image, it will be changed to light red simultaneously. And we are using this perturbation function shown as this vector field in the CL with color space. So why this functional adversarial example? So why don't we just use the already made additive perturbation? It's because if we use this global uniform changes, so let's say we change all of this color to the uniformly change from this vector field, it will be much more less perceptible. And then when we already optimize this adversary attack, we can also combine with the existing additive models and also combining it with the other attacks for most potent attack, even for after adversarial training. And also this recolor adversary specifically can significantly reduce the accuracy of ResNet32 model. ResNet32 model is a residual network model that is trained in the CFAR10 dataset. So this is how the victim model that we are going to attack looks like. And this is how it looks like in a deeper residual function. And yeah, so the idea of this whole assignment is to use this adversary attack by comparing the PGD and the CW attack. I'm mostly gonna use the CW to optimize it as much as possible within the given time. So I explored using the data manipulation. So I will adjust the input data first before I enhance the model in any way. And then I'll also change the batch comparison. So, and then next I applied gradient clipping and accumulation, which relates to the momentum as well. So basically, the managing gradients is to prevent the extreme values and improve the attack efficiency. And also using momentum is to enhance the attack's stealth and effectiveness. Okay, so we can now jump to the demo. I already cloned everything in my Colab in here to save some time. So I clone and also import the necessary libraries. And I can see them already loaded in my variables in here. And this is how our image will look like. So if we just load this CFAR data, basically we're only taking 16 per batch. So in this batch, we only have 16 image and it will change for every session runtime. And I also load the ResNet32 that I explained just now, this one, into this Colab and also the normalizer. And yeah, this is the image that we are going to use in this batch. Okay, so for the first modification that I did for Milestone 2, basically this is based on the theory. By increasing the similarity between the neighboring pixels, in theory, if we increase the number of pixels and apply more bluing, it will be even more undetectable by the human eyes and lesser absolute difference as well. So making it undetectable for the detector or the classifier as we increase the similarity between the similar neighboring pixels. And also in here, it's important that we are using the CLUF color space, which is on the left side here, this one, instead of the RGB. So basically, the RGB color space results in a noticeable bright green artifact and the adversarial example, while the perceptual accurate CLF color space produces a more realistic perturbation. That's why I'm using this color space. And CLF actually presents a color by 3 components. So this is how the CLF color space looks like. It's basically just how we project the color. And this is RGB. And CLF presents a color using 3 components, which is the L, U, and V. L is the luma, while U and V together define the chroma. So CLF allows us to regularize the perturbation function F, this one, perceptually accurate. And also, this is the perturbation function that we are going to use in here, and it will result to this perturb output. And then we also need to use the CW loss F6 specifically. And also we solve the Lagrangian relaxation for the smoothness. And it's replaced by an additional regularization term, which is this one. So this is all can be refactored to the code that I implemented. So this one is for the input data enhancement. So basically I just make it a Gaussian blur with a certain radius that I can change and also resize it. And then we load this again. So if we load it and then we look into how it looks like, then this is the data, the batch, the 16 batch data that is inputted to here. Okay. And then for this one, I just put the data into the PGD attack that we are using. So basically the usage of this is that we're using the CLF color space. And then this is the CW loss that I was talking about. And this is the loss and also the regularized code. And then we just fit all of these into our mode, become like our model's attributes. And this is our attack object. And when we want to attack, we need to fit in the examples. So in this transform example, I'm using this variable and I have recorded the result if I to use that examples transform. Basically, it will result in a better attack. So what it does is that it will make the original accuracy goes to 12.5, which is very, very drastic because if we don't use this modified data, then the model will usually have 85 to 100%. So going to 12.5 is quite drastic, and it might incite some suspicions as well. So that's not what we want for this attack, as we want to make it align to FIT3183 theory to make our attack to be unpredictable and undetectable. I will not be using this data enhancement. And when we don't use it and use the examples itself, the examples is this one. The examples is this one. The results is actually making much more sense. So this will gives us the original accuracy to be 100, which is the performance of the ResNet without the perturbed data, which is correct, because as we can see from the result of this ResNet is actually really, really well. But the adversarial accuracy is 0%, which is actually too good to be true, and it might also inspire suspicions. So what I want to do for this whole assignment is I want to increase this just by a little bit. And yeah, also for using this this code, I also applied the ADAMW as proposed by Lightbazier. But as we can see, the attack is actually only helping a little bit up from there. And this one is using the original examples transform. So previously it was 12.5% of accuracy of the original. And in here it's 25. So it's only helping it a little bit, and it doesn't really help much in general. That's why I will just stop using this one, because it's not really helping much. And yeah, so from the milestone 2, I conclude that I'm not going to use this input data enhancement, and I'm also not going to use ADAMW. And that leads me to modification for part 1 in assignment 3 or the milestone 3, which is I'm using CW attack because all this time, the author of this GitHub is using PGD for the collab. So now I want to use the CW attack, which is already in the GitHub, but it wasn't working. So I need to edit a lot of code to it and also utilize some of these approach that I believe will increase the accuracy as well. Okay, so first I will explain on utilize the logical knot. So basically in utilizing the logical knot in here, it is just, okay, let me show you how it looks like in the code in the back end. So this is the code of the back end part. So logical knot in here, okay. Basically, this logical knot is in the batch compare function. And I will explain the code. And in here, the logical knot is actually giving the knotting to the Boolean tensors of max targets. So this max targets variable is a Boolean tensor indicating whether the predicted class matches the target class. And the logical knot inverts these Boolean values, turning true to false and vice versa. While initially, it actually used 1 minus the max targets, subtracts the Boolean values from 1. So effectively inverting them, since true is treated as 1 and false as 0. But using a logical knot is generally better because this function is optimized for logical operations on Boolean tensors. It is likely to be more efficient as well than performing arithmetic operations. And also, it's much more readable and for type safety. So this function is designed to work with Boolean tensors. It ensures that the operation is performed correctly and safely on the Boolean values. And also, this function ensures consistency in the code base when performing logical negations. It aligns with the other logical operations provided by PyTorch. Okay, so I will show you the results of using that logical knot. Basically from that, from these backend code, it will be applied in here. So I just need to call this function, the CW, that already has the batch compare just now. And then I will not be using examples transform. So basically I already recorded this, the batch that I did using just the examples itself. So the logical knot actually increased the number of successful attacks because previously it was 11 out of 16. Now it's 12 out of 16. So it performed well for this case. And then I also applied the gradient clipping. So basically for the gradient clipping, I will show you how it looks like in the back end as well. The gradient clipping is in here. So the gradient clipping is in the optimize step function. And I will explain the function one by one per line. So we have the zero gradients, which is the optimizer dot zero grad. So it clears the old gradients. Then we compute the loss using the loss function forward pass. And then we use the backward pass. So it computes the gradients of the loss with respect to the parameters. And then we also have the gradient clipping. So this gradient clipping clips the gradient to prevent them from becoming too large. Then the optimizer step updates the parameters of the perturbation using the clip gradients. After the gradient clipping, the optimizer step function will use the clipped gradients to update the parameters of the perturbation. So this helps in stabilizing the training process and prevents the optimizer from getting stuck due to excessively large gradients. So, okay, I will show you again how the usage looks like. Okay. So I just need to call the Carlini-Wagner and then initialize the attack object in here. So once I have the attack object, I just need to attack it with these parameters, and I can change these values as well. And basically, I can do a simple run for now. Simple demo using the examples. Okay, so now this is all using examples, examples, and examples. Then we can run. So CW attack is actually using the binary search step. It's looking into the loss values that is most optimal between the trade-offs. And to save some time, I actually already recorded the output. And using the example transform from the Milestone 2, it is actually not that bad because it increased the number of successful attacks to 14 out of 16. But the original accuracy is still very low, which is very suspicious. But the adversarial accuracy has increased to 12.5, which is not bad as well, but not really a nice approach in this case. So I'll just using the examples from the CFAR without doing any blurring or resizing. So I did two batches in here. Both of them did pretty similar. So it's around 93.75% for the original accuracy. This one is without the perturb example, and this one is with the perturb example. So we succeeded in increasing this to 6.25, and we attack 12 out of 16. So that is quite good. And we also see in here the difference between the original and this one is the perturbed images. It is not very visible by the human eyes, but if we just use a magnifying difference in here, we can see some of it are quite different to another. And I see that some of this actually has quite visible changes in this part. So I want to minimize this and still achieve similar results for this. In that case, I also tried to increase the binary search step. In here, I increase it to 20 and like 30. So it will have a lot of more iterations on the binary search, but the result was not very significant. So it does not increase the performance very much. So it's not worth the computation time. Okay, so let's see. Okay, binary search step 5. This will go on until search step 9 because it starts from index 0 and I have 10 search steps. So it's gonna stop at 9 and I will pause this recording and start it again when it's done. Okay, so now the model has done the attack. It's finished the attack. And we see that it's now only doing 8 out of 16 examples as successful attack. This is because we rerun the examples batch. So we have different result from the batch that I did before in here. And basically, if we see the result, then 87.5% is correct from the classifier, and 6.25 is from us, from the perturbed adversary attack. So this is quite similar to the result in here. The stats are pretty similar, and even the stats for the adversary accuracy is the same. Okay, that's for the demo for this one. And then next, I will show you my part 2 modification, because from here, I see that there are quite a huge change in the adversary perturbation. So I want to minimize this, but still have the similar results. Okay, so I will show you how I did that. Okay. Okay, so this whole idea is actually based on this theme in the ad forum. Basically, what I am doing is I want to have the model has similar output by also decreasing the iterations and the momentum, which something that I will apply in here. Just the momentum. The momentum helps by smoothing out the update direction, leading to more stable and efficient perturbations, while the gradient accumulation ensures the smaller gradients are built up over time, reducing the chances of vanishing updates. So I will show you the change in my local IDE. So basically, for the momentum, I add another part here. Momentum. Okay. So the momentum, I feed it to my optimizer, optimize step function. And then I also need to add this iteration at variable. And this is the momentum. So basically, this is the difference between the one without the momentum and the gradient accumulation, and this is after I change it. Okay, so I will explain. And after doing this, I also need to apply the evaluation to see the actual difference and if this is a suitable modification or not, or if it's actually working. So that's why I add another function beneath this one, which is the evaluation. So this evaluation, I use the L2 norm and the Linf norm from PyTorch, and I do that for both of the attack without the modification and for the attack with modification. Then I output it in here, and then I also use the parents class in evaluation. So the parents class has its own evaluation methods. So I'm just using it in here, and I will display how it looks like in the collab because I also uploaded it in the collab. So basically, this is the parent class, the adversarial attack. And this is the evaluations functions, and this is my CW modified. Okay, so now that I have the CW modified and the evaluate function, I just need to run this. This will take about 30 to 45 minutes to run because I need to run 2 CWs. That's why I already ran it beforehand. This is the result. So I will just explain how the result is. Okay, so for the L2 norm, there is a difference of L2 norm in the modified CW has a lower value about 0.7048. This indicates that the perturbations introduced by the modified attack are on average smaller and in magnitude compared to the original attack. And the L infinity norm, the modified attack has a slightly lower L infinity norm by approximately 0.0076. This indicates that the maximum perturbation to any single pixel is slightly smaller in the modified attack compared to the original attack. And we can also see that from this plotted image. So we can see the changes in here. The original CW is actually bigger than the changes in the modified one, and also similar to this part here as well. And then we also have the accuracy. So after the changes, we want to see if it is still accurate. And both of them are actually good at it. And the original CW has about 25% accuracy of the adversary being correctly classified by the ResNet, while the adversary accuracy is actually more efficient because it could reach to 12.5, indicating that it was more effective in fooling the classifier compared to the original attack. So even though we applied lesser changes in here, it was actually more effective than the original one. Okay, so the perturbation magnitude for the modified CW was smaller, as we can see. And this is what I want because it makes the adversary example less perceptible to the human eyes. And yeah, so I can run this and I will pause the recording again. So this is my demo for my last update, for my last enhancement. Okay. And we can see from the previous result that I showed just now, the modified attack achieves a better reduction in accuracy in the smaller perturbations. So this indicates a better trade-off between the effectiveness and perturbation magnitude. And so overall, it was a good result because the modified CW attack achieves a similar reduction in accuracy with the smaller perturbation. And this indicates that the modified attack is more efficient in terms of perturbation magnitude while maintaining its effectiveness. Okay, so I will pause the recording here because this will take quite long. As we are waiting for the model to run, I will explain how we can actually use this optimized functional attack for the using it combined with the additive adversarial attack. So basically, this is how it looks like. It's quite similar, but then we can also apply the other attacks in here. So I can just run. And also, this is the pre-built attacks. Basically, we can also use this pre-built attacks. So this paper actually has this recolor adversary and the standard adversary and delta. So by combining these, they're able to achieve better results in here. And you can also have more number of successful attacks, which is quite nice. Yeah, that is all for the explanation of this whole collab as we wait for this one to run. Yeah, and I hope my collab is detailed enough to explain what is happening in here. And yeah, I'm open to answer any questions. Okay, I will pause the recording again as we wait for this one to run. Okay, as we can see now, the code has finished running. And let's see the number of successful attacks. Okay, so both of them has the same number of successful attacks, 9 out of 16, which is around the same or actually improving from the attack in here. Yeah, it actually improved by 1 from the one that is using the modification from part 1. And as we can see, the values are actually also similar. So as I explained just now, it's actually good because the modified Carlini was able to give lesser change in the perturbation, but actually achieve around the same accuracy from the original CW. Okay, so successful. So to conclude, my modification in Milestone 2 also worked, but it's not a really wise selection on this approach, on the attack approach. And also for the modification for Milestone 3, so the CW works well, and also these two addition improve the model, and also using the momentum and gradient accumulation is actually improving, as in we don't have to change the input so much while also achieving similar results. So in this case, I've enhanced the attack. Okay, thank you for paying attention so far. And that is all from my demo.